from uh, from the previous class. All right, so now you have you have, you know, you can go to the link right here, right? If you just open your laptop or something, um, if you cannot see what I'm writing on the board. All right, so now let's do this. Cosine. AB, AC, this is AB, 1, 4, -2, this is AC, -5, 4, 1. When you consider AB, AC, we need to follow this product. So it's first S1, Y1, so you have 1 times -5 plus 4 S2, Y2, so you have 4 times 4 times 4 plus 6, -2, 1. Yeah, divided by, you know, the norm is root of, I already got that. The norm of AC is 95. All right, so that's the answer for the angle. We need to do some computation right here. Now let's see. So that I'm doing everything correctly. So we had -564. We see 59 plus minus 12, we see 47. All right. So I hope that is correct. All right. So now you get into the final answer. So the final answer now is maybe a bigger. So now the final answer we have is 1/2 root of 89, 95. Psi, remember that everything right here, you need to make sure that yeah. And the final answer to the question is this from question 39.52. Yeah.
Tàu Quang Khang Destroyer nghỉ rồi. Ủa nay không có tàu Quang Khang Destroyer nữa.
Is it all right? Can you do us questions? All right, so let me do the second question. Let me do the second question.
Không ý là nó vẫn phải học đi học không được thì không được được đi thi cái thế nào nếu tầm này mình master chứ thì cuối cùng vậy đó cô rồi này thôi
cái equation của đường AB với lại AC là từ đâu tại sao nó lại như thế này?
Yeah, so that's the definition we use, the standard definition. When you have A B, when you have A B C and B D E F, then we define the vector AB using the standard way. So this is what we're supposed to do, right? Yeah, it's just the definition. It's just definition. Yeah, we accept this one. We accept this one as the standard definition, and we go for the question. And when you do the norm, you need to follow the product given in the question. So AB right here is in my question. AB is 1, 4, -2, right? When you do 1, 4, -2, multiplied by 1, 4, -2, then to apply the product. S1, Y1, you can see the definition in this. S1, yeah, so sorry, this is S1, S2, S3, this is Y1, Y2, Y3. How to define this? The answer is given in the question. You consider S1, Y1 plus 4S2. That's why you see this. That's why you see this. S1, Y1, 1, 1, right? S2, Y2, 4, 4. Yeah. Just from this. Yeah.
bấm máy đi. Tao móc cái máy tính này tao bấm mà ra đáp án là tao để đâu mày. Bấm đề mà chứ sao đề tao có làm.
Is that right? So let me go to the second question. Now, this is still from inner product spaces. You have you have so let me go to that. The second question. Second question. V is the node space of A. Last time I already defined the node space. Let me remind you what the node space of A is. The set of S. Right here, you would know that. I should write it in this format. It's a column vector because A is 2 by 4. AS is, so the node space is just the set when the set of S so that AS equals 0. Yeah, that's the definition. That's the definition. All right, so definition. A is 2 by 4, S is 4 by 1, right? So when you consider AS, you get a 2 by 1 matrix. Now, let's, one thing I think I mentioned last time is a formula, or you can say a fact. Rank of, sorry, dimension of node space of A is equal to n minus rank of A. So let's say this is formula 1. What's the n? N is the number of columns of A. So let's say A is a n by n matrix. The number n is the number of columns of A. All right. Do you know this formula? So let's say formula 1. All right. Now, when you consider the node space of a matrix, it has nothing to do with inner product spaces, right? So this is just a concept for vector spaces. You don't need an inner product in order to define the node space of A. Remember that. Yeah. This is, you can say this is from vector spaces only. And now I have another formula. Let's say formula 2. And second formula, we have a thing related to inner product spaces. That's dimension of V. Maybe I write it in a different area. So let me write it right here. So let's say this is formula number 2. Let U, maybe S or something. All right, so let's say U be a vector space space. All right. Let V be a subspace of U. Then we had just of V plus dimension of V is equal to dimension of U, the bit space. Orthogonal. Do you remember the definition of V orthogonal? Let me remind you what the definition of this is. Definition. The notation and the name already say something, right? V orthogonal is the set of all vectors in the bit space, in the whole space, U, let's say, so that they are orthogonal to V. Let me write the definition. So they'll say the set of, let's say, S in the base space U, so that S is orthogonal to V. When you say S is orthogonal to V, you probably want to say S is orthogonal to S in V, right? That's the definition. When S is orthogonal to every vector in V, you say that S is orthogonal to V. And the set of set S is defined as V orthogonal. This is also a subspace U. And the formula we have right here, the formula 2, is that the dimension of V plus the dimension of V orthogonal is exactly equal to the dimension of the bit space, the whole space. Yes, that's enough of the theory. So let's go to question number 2 and see how to get the answer. All right, so let's do the second question now. All right. Let's say A, right? How to find the dimension V orthogonal? According to this, you only need to know the dimension V, right? Because the whole space here is R4, right? U is R4, the base space, and the dimension of that is 4, right? So if you know the dimension of V, you know the dimension of orthogonal. Yeah, you don't need to find V orthogonal. In order to find the answer right here, you need to. All right, so now it's time to write exact f of V. This here, what's the dimension? No space of A, right? Because V is the no space by definition. And it's 4 minus rank of A. Let's say from formula number 1, right? And now you only need to know what's the rank of A, and it is obviously the number 2, right? Because A is already in echelon form, right? So now you get the answer for dimension of V orthogonal. I would say since this is what we have from formula 2, right? So dimension is 4 minus 2, right? So this is 2, this is 4. So this is the final answer. Is that right? Now let's go to this input a basis for V orthogonal. You know that for any vector space, we have not only one but infinitely many spaces, right? Therefore, right here you can, we had many answers for this. You only need to input a correct basis, but we know that let's say for this one we don't have a unique answer. How to do this? You know, in the first part we don't need to do anything, right? We just apply some formulas. But now we need to do some computation right here, right, in order to get a basis. I think in order to find a basis for V orthogonal, first we find a basis for V, and from the definition right here, you can get a basis for V orthogonal. So first we find a basis for V, and then we get a basis for V orthogonal. Now let's do it. So for the second part of the question, V is just, from solving, let me write like this for simplicity. If you want, you can put it as a column. AS equals 0. Remember the definition right here for V. AS equals 0, right? So let me write it in a more as a system right here, right? So we have S1 plus S3 plus S4, S2 minus S3 plus 2S4 equals 0, right? Let's see what we got. We get from AS equals 0. All right, so now to solve this one to get a basis for V first, right? Solving this is very simple because the matrix right here is form you don't need. We set 2 free variables. Of course, we do for S3 and S4. So we set S3 and S4 for free, right? We may use TS, if you want, you can keep S3, S4, it's not important. Let me write TS, and then you get S1, S2 from these 2 free. So from here, you get S1, and from the second line, we can get S2 with the T minus 2S. Is that right? And now you had this minus T minus S for S1, T minus 2S for S2, T for S3, and S for S4. In order to see a basis from here, you take T and S out, right? That's the normal way we do. We write T right here, and then we have this one inside, and we take S outside. We get this, right? Do you see that we can write from here to here, right? They are the same, but the way we write in here is for getting a basis for V, right? So we take T out, so we had negative 1, 1, 1, and 0. We had no T in here, so we had 0. And then we had S right here, we had negative 1, negative 2, 0, 1. So they are the same, right? They are the same, but now you can see you can see a basis for T, for V. So what we get right here is this is a basis for V. And it's time to get a basis for V orthogonal. So V octonal is um, now remember that what you do so far is just about vector spaces. Yeah, we haven't used the given product yet, right? Because you right here, you just get a basis for V, and V is the node space of A, so just from vector spaces. But now it's time to use the product right here to get a basis for V octonal. So by definition, you know the definition of this one. V octonal is, let me remind you, is the set of vectors that are octonal to V, right? So you have, let me set a vector S so that S is octonal to V. This is the definition. But when you have a basis, you can translate this one into the set of S so that S is octonal to, let's say, V1 right here. Let me put this one as V1 and this one as V2. So you can write this, yeah. Because if a vector is octonal to a basis, it's octonal to the whole space, right? Because you can write any vector in V as a linear combination of V1, V2, right? Therefore, when you had this, you have S octonal to the whole space V. So, all right, so from here we can get the answer. So let's say S is S1, S2, S3, S4. Now, any questions? So let's do the next question. We have only 4 questions, and I think I can do all questions today. So let's go to question 3. Now, so let's so right here we find m, so that the distance from this vector u minus m1 negative 1 to v is equal to root of 7 over 4. How to find the distance from a vector to a subspace? How to find that? Let's say you have a subspace V right here, and you have a vector. Let's say this is your vector. Let's say U. When you draw a vector, you can imagine that as a point if you want. So a point right here is a vector. Or if you want, you can identify this with something like this. We see more, natural, right? But sometimes it's easier for us to look at a vector as a point. You can, switch between the two. A vector is, a vector you can imagine is a point in 3 dimensions if you want, because when you have a vector, we had 3 numbers attached to that, so you may consider it as a number if you want. Anyway, so how to find the distance from a vector to a subspace? One way is that you look at the projection of that vector into the subspace. Yeah. So you find M first. And then you evaluate the distance right here to get the answer. That's one way. Yeah. So if you want to get the distance from a vector or a point to a subspace, first you find the projection, and then you get the distance from evaluating this one. Another way is that I think you already saw this one from the previous class, right? Anyway, so another way is that, let's say you have a point, or if you want, you can consider this as a vector. Another way is that you look at any point right here. Let's say n, you find the distance un, and you find mean of this one. Yeah, mean of un for n, a point in V. Yeah. So now the distance, the answer is mean of this one, right? For n is a point in V, right? When you consider mean of un for n in V, you get exactly the answer for the distance, right? Yeah, we had some different ways to get the answer. So let me say again, the first way is that I think this is the most obvious way to find the distance. First, you find the projection, and then you evaluate the distance from the point to the projection. Or you can find the distance by considering the mean of un for n going on the subspace V. Anyway, so let me do the third question. The first thing we need to do is obviously to get a basis for V, right? Find a basis for V first. So V is the node space, so you have V is the set of S1, S2, S3, so that AS equals 0. So we have S1 plus S3 and S2 equals 0. Right? AS equals 0. AS is S1 plus S3, S2, right? And from here you need to solve this one and get a basis, like we did in question 2, right? So when you look at this, we have S3, a free variable. So you may write T, 0T, T, any, right? Any number. So you set, because, the rank of A is 2 and you have 3 unknowns, right? So the system has infinitely many solutions depending on one free variable. 1 because you have 3 minus 2 equal 1, right? And you set T for F3, we see 3, right? So you get this one. And now from here you get If you want, you can write like this and get a basis, right? So this one is now. So let's go to the maintain. Find the distance from U to V. In fact, we find a number m so that the distance from U to V is root of 7/4. So I think I'm going to apply the second method. I'm going to apply this one. So let me do that. So I write the distance from U to V is this one. This is what we want, right? This is the same as mean of U minus V yeah. So you want the distance from U to V to be equal to this number. Then of course, mean of the distance U minus V, right? So yeah, so let's see what you have. Let me, let's say this is U, right? And V can be any in here. V can be any in here. So you have so many V, right? You have so many V. But the one that's, remember that this is your subspace V. This is your subspace V. But the one that's minimized this is the answer for the distance. So V is right here. This guy is the one that minimized UV, right? So if you look at this one, you will see this is U minus V. You look at this one, you see the norm U minus V. But anyone in here would be greater than this guy, right? So this guy is the one that minimized this. All right, so this is one way to do the question. You don't need to look at the projection. So we have so many V, so many vector V in the subspace capital V. So we have so many distances. U minus V, right? The norm of U minus V. But the one that minimized that, the norm of U minus V is the answer for the distance. So let me go for this and get the answer. So from here, I just go for this one. Maybe I go down right here. So if you consider the number here, you would have the square root, right? In order to remove the square root, you can square both sides. So this is the same as, let's put the square right here. Because, you know, it simplifies your computation. When you had the norm without the square, you had the square root, right? Now you have square right here, you don't have the square root. So it's time to get the answer from here. All right, so what we have right here is, look at what we have right here. So this one is exactly, first, what do we have for this? U is minus M1, and V is in the subspace V, so it should be in this form, right? So because V is in the subspace V, so you have a vector in this subspace given by this. So let me write minus t, 0t. So that's what I have for a vector in the subspace V, right? And then you can write this one as, so you had t minus m, you have 1, and you have minus 1 minus t. Is that right? And then from here you get u minus v, the norm of u minus v squared. So it's t minus m squared. Now it's time to use the product. Yeah, so when you do the norm, you need to use the product. So by the way, let me write v minus t, 0t. So you have s1, y1, so you have s1 square, right? s1, y2, s2, y1, so you have plus 2, t minus m, 2 plus 2, 1 squared, and plus 3 minus 1 minus t squared. Yeah, so I'm not sure whether you see this, but what we are doing is just to get the norm of u minus v, and v is a vector in the subspace V, so it should be minus t, 0t. T can be any number, right? So from here you have, yeah, you use the norm right here and you get to this one. Maybe I simplify this a little bit. So let me simplify this a little bit so that we can all right, so this is exactly the distance we have. And if we simplify this, we get something. We say 4t squared plus 8t. Yeah, it's not, maybe I keep this one. Yeah, I don't think we need to simplify this. Yeah, keep this one right here. All right, so now you can say the next thing we do is now the mean of this one, must be 7/4. But when does the mean happen? You know, the answer is when the derivative of this function equals 0, right? So let's say this is f of t. So mean f of t for t is any number because v in the subspace v, it means t can be any number. So mean of this one happens when f prime of t to be 0. Yeah, because v is the variable, right? V right here is minus t, 0t. V is any vector in the subspace V, and it's given in the form minus t, 0t. So in order to, you know, get the whole space, t can be any number. So the variable right here is t, not m. You are finding mean with respect to V, but V is given by t, right? So t is the variable, not m. All right, so from here, you only need to differentiate this one. yeah, I think that's the way we go, right? So differentiate this with respect to t and see what we get. So let me do that right here. I differentiate this one with respect to t, t derivative, all right? Maybe I simplify this a little bit. So I get 8t minus 2m plus 8 equals 0. So that's what I say. And now, it means t is m plus 4 plus 1, right? Plus something right here. Maybe I write over 4, right? Right here we have minus m 2m minus 8 over 8. Yeah, so that's what we had. All right. Now let me go back a little bit from the beginning. Not so beginning, but I focus on this one. So the question is just to find m, so that mean right here is exactly 5 over 4, right? But we know that mean right here is mean of f of t, right? F of t is exactly u minus v squared right here. We get that, right? And now we know that mean happens at t equal m minus 4 over 4. Now, how to get the final answer? So I think you can do this and get the answer. Now you insert this one into this. Yeah, insert t equal m minus 4 into this one and solve the equation right here. All right. So now you this is what you do. So insert t m minus 4 over 4 into u minus v squared, so that you get, let me do that right here. I only need to insert so I get this one. Maybe I simplify this a little bit. So I get this number. Yeah, so of course you need to do something right here, right? So maybe I write it right here. So I say that from here you get m, right? All right, so that's question 3. So let me do the last question also. For that, we need to know something about uh, the the almost last chapter we have in linear algebra, linear transformations. For this one, I would say it's not a big thing right here. Let's say a linear transformation. It's just a map from two vector spaces. Let's say V and W, so that it satisfies these properties. Right here, you can see some examples. So right here, for example, right, this guy T is from R3 to R2. R3 is V and R2 is W. You can easily check that we had these two properties for this map T. So they see a linear transformation. Yeah. Maybe I do only the second property. Let me show you. This map satisfies the second property. Of course, this one is also all right with the first property. Therefore, they say a linear transformation by definition. We see linear transformations in many problems. For example, if you consider the rotation of a vector, that's exactly a linear transformation. Anyway, so let me consider only the second property and show you that this guy satisfies this property. And then I go for the last question right here, question number 4. All right. So for the theory, I think you can read the note. That's it, a very short note, right? 2 or maybe 1, 2, 3, or 4, 5 pages. Now let's what I'm saying right here, all right? So let's see why we had just a linear transformation. I do only the second property. So if you consider T, K, U, you need to make sure that it's the same as K to U for any number K and any vector U in your domain. The domain is V, right? So let's say U is S1, S2, S3. When you consider KU, you know it's KS1, KS2, KS3 by definition of R3, right? When you multiply a number by a vector, you get this one. And then you get T, KU is T, KS1, KS2, KS3. But by definition, T, KS1, KS2, KS3 is equal to KS1 minus KS2 plus KS3 and 2KS3. All right, so you get this one, T of KU. Now let's see whether we had this exactly equal to KTU. If we had that, then you know the second property is correct. And you know that's what we have. So let's do KTU and see what we get. K is a number K, right? TU is T, S1, S2, S3. T of S1, S2, S3 is given by this formula. But now it's time to write this as KS1 minus KS2 plus KS3. You can write this because, you know, in R2, when you multiply a number by a vector, you can, you can do this. And now you can see they are exactly the same, right? This one is exactly the same as this one. It means that you had this property, right? Yeah, so you can read more in the note. I'm not going into that. Yeah, so let me go to question 4. Now in question 4, you have this linear transformation. You don't need to worry about whether there's a linear transformation. Yes, it's a, if you don't believe that, you can check using the definition. And then you had two bases, E and F. E is a basis of the domain R3, and F is a basis of the range we see are two. The first question is find the transformation matrix of T relative to the bases E and F. You need to know the definition of this one. And the definition is quite simple. You only need to first evaluate T of E1, and you find the corners of that in the basis F. You put that into the first column. Yeah, you can see one example right here. You evaluate T of E1 using the formula you have of T. You get this vector. Yeah. And then you find the corners of this vector T of E1 in the basis F. So, that's an obtain rate. You get the corners 1, 0, 1 over 5. And you put these corners into the first column 1, 0, 1 over 5. All right. You do the same thing for E2. You evaluate T of E2. Of course, using the formula you have T. Then you get this vector, and then you find the corners. Find the corners of T of E2 in the basis F. So you get this one, negative 2, 2 over 3, 4 over 5. Put that into the second column. Yeah, and that's the end because you have only two vectors, E1, E2 in the domain, right? Yeah, so that's the definition we have for. So the question is, why do we need to consider linear transformation matrices? The answer is, you can use the linear transformation matrices to find the corners or to do, to simplify computation, let's say. So you can see some properties right here. I'm not going to prove anything. You can see them right here. So let me go to question number 4 and do the first one. I think we don't have time, so let me do this a little bit faster. So I go for A. So for A, you can see we want to find T from E to F. So you may need to read the definition or look at one example right here. But I think in order to find this, you only need to use some properties you see right here. So I think I can do this one by, first I look at S. When I write S, I mean the standard basis. Yeah. When I write S, I mean the standard basis. So you can find the answer right here by looking at the standard basis because, always simple in that way. So I can go for, from E to S. All right. So how to go from E to F? First, you go from E to S, and then you need to go from S to F. So you need to write P, S to F. Do you see that? Right here, or right here? Yeah, so let me do it again. Let me do it again. First, I see that we go from E, right? So I need to find for this one, E to S. But then we need to go from S to F. I need to write P from S to F. We need to write P is the transition matrix from S to F on the left. Write it on the left of T. So now the one right here, you can see this one is right. E1 is E1 is this one. So I need, yeah, let me say it a little bit fast. So this is the basis E, right? This is E1, this is E2, and this is E3. You want to find the matrix of T from E to S. According to the definition, you only need to find T of E1 and you put it into the first column because the corners of T of E1 in the standard basis is exactly the same as T of E1. The same for T of E2 or T of E3, right? So, and for this one, you know, yeah, there's an althane, right? You only need to write P, F to S, take the inverse. Yeah, um, so for the second part of question, we have, yeah, so we find the corners of TV in the basis F given the corners of V in the basis E. So for that, we can use this formula. So you have you get this one from this, right? And VE is given in the question, so it's this guy. Yeah, so that's the second part of the question. Now let's go to C. Yeah, again, for this question, we can use one of these two formulas to get the matrix for T. Now let's see. Right here, we want to get T from G to F. And we know from P right here is the transition matrix from the basis E to G. Of course, now you go for this one. Yeah, you may say, all right, let's go for T from G to E, but it may be better if we use this formula. So instead of write T right here, we may write P. Yeah, we had two formulas, so we go for P. Yeah, because we are given this one in the question, right? In the question we have from E to G. So if you go from G to E, the same, take the inverse, right? So this one is just the inverse from E to G. So basically, we have from G to E, and then we need to go from E to F, right? So we put T right here on the left. And again, this one is already from the first part of the question, right? And this guy we are given in the question. Yeah, so that's what we have for the third part. So we had two formulas, and you can see in C we can apply this one. So let's go to the last one. Input a non-zero vector in the kernel of T. So let me first give the definition for the kernel of T. By definition, there's a it's the set of S in the domain, so that T of S equals 0. 0 right here is the vector 0 in the range. So in the question we have V we have is R3, right? So you have a vector in V given in this way, so that S1 minus S2 plus S3 0, and S1 minus S2 is also 0. 0 right here is the vector 0 in R2, the range. So yeah, so now you can input any vector so that it satisfies the system. I think I can put 1, 1, and 0. That's all right. Because 1, 1, 0 is a non-zero vector, right? It's a non-zero vector, and it's in the kernel because this one satisfies this system. So, of course, this is not the only one. You can put, for example, 7, 7, 0. That's also all right. Yeah, we have so many vectors in the kernel. The question is just asking for one vector, right? We see non-zero vector. All right, so I think we stop here for today.